So basically, just imagine for a second, uh, billions of light years away, two black holes, each 30 times the mass of our sun. They are spiraling towards each other, and for billions of years, bleeding the energy into space and getting closer and closer to each other. And then, less than a second, they crash. Now, this collision radiates more energy than every star in the observable universe combined, but not as light, but as ripples in space-time itself. Now, this ripple travels billions of light years and arrives at a machine that we built in a field in Louisiana, and we caught it. So today's video is basically about how we detected the gravitational waves using a LIGO, and we'll discuss about it. So now let's get into the video. Now here's basically the roadmap on what we'll cover in this video. It has basically 8 sections, and each one is built onto the next. Now, the first aspect is the physics aspect, in which we talk about what gravitational waves are and what generates them. And then is the LIGO, which is the machine itself which detected the gravitational waves. And then is the DSP pipeline, and then noise, the three frequency dependent phases, and then match filtering, which is arguably like the heart and the core of this entire video, and then advanced DSP, including one trick that cheats quantum mechanics itself, and then the first detection and what comes next and what is the future of it. First is the physics aspect. So then, before we detect gravitational waves, we should probably know what gravitational waves is in the first place. So Einstein had published general relativity in 1915, basically telling gravity is a curvature in spacetime and not just a force like how Newton had predicted. Mass is curved spacetime, and curved spacetime basically tells mass how to move. And a year later, he had found accelerating masses must disturb that curvature, sending ripples, which are now called as gravitational waves. And these travel at the speed of light. Then he had spent years arguing the fact that it's probably just mathematical and not even real at that point. But he was actually wrong, and it took us 99 years to prove it. Now we'll understand what gravitational waves are actually. So gravitational waves are nothing but ripples in space-time, not through space but off space itself. Now it stretches from one direction and squeezes perpendicular as it passes. When two black holes orbit, or gravitation requires them to radiate energy as gravitational waves, the energy drawn from the orbit itself. Now this orbit shrinks as they spiral faster and they radiate more and more energy. Now this emitted signal is called a chirp signal, which is sweeping upward in frequency and amplitude to a merger, then ringing down like a stuck bell. It actually sounds like a bird chirp, which is the reason why it is called a chirp signal. Then comes the strain aspect. Strain is nothing but fractional change uh, the wave causes and is written as h equals delta L over L. Now, for a merger a billion light years away, h is roughly 10 to the minus 21. Now, in human terms, the LIGO's 4-kilometer arms move 4 times 10 to the power minus 18 meters, 1,000 the diameter of a proton. Spacetime is extraordinarily stiff. It takes the most violent events in the universe to produce even that tiny a ripple. Now we'll understand the Einstein's equations, which led to him understanding what gravitational waves are in the first place. Now, the Einstein's field equations are nothing but 10 coupled nonlinear differential equations relating curvature and to mass and energy. Now, when we linearize them, and a wave equation drops out, which is radiated power proportional to the third time derivative of the mass quadruple moment, a symmetrically accelerating mass. A perfect sphere spinning in place radiates nothing. Two black holes spiraling towards each other radiate enormously. Now, the LIGO's main target is binary black holes. Over 100 have been detected till now. Uh, but the most richest target, I mean, in the sense like which give us more information, are basically binary neutron stars. In 2017, we had caught gravitational waves and gamma rays from the same mergers simultaneously. Two messengers, one source, one moment, never before in astronomy. It's been confirmed that gravitational waves travel at the speed of light to 1 part in 10 to the 15th. Now, other sources like that we would predict, which would help in prediction, are supernovae, extreme mass ratio in spirals, and etc. etc. Now we'll talk about the machine that had made it possible to detect gravitational waves, which is LIGO. Now, LIGO is nothing but a microwave interferometer. The laser basically splits at a beam and splitter, half down each arm, and it reflects and recombines. Now, equal arms make perfect destructive interference. I'm sure everyone's heard of this term. It's used in active noise cancellation and all. And now, because of this perfect destructive interference, the detector sees darkness. Now, a gravitational wave stretches one arm and squeezes the other simultaneously. Now, this cancellation breaks and light leaks to the photo detector. That sliver of light is nothing but a gravitational wave. The actual LIGO is far beyond a textbook microscope. Uh, the cavities bounce laser 280 times per arm, basically 1,120 kilometers of effective path. Now, the power recycling boosts 150 watts to 100 kilowatts of circulating power. More photons means better statistics for us. Now, the ultra high vacuum is of the order 10 to the minus 9 torr across 10,000 cubic meters, which makes it the largest vacuum system on Earth. Now, the 40-kilogram fused silica mirrors hang on quadruple pendulums, four cascaded mechanical low pass filter stages, plus active seismic isolation, together attenuating ground motion by 12 orders of magnitude, and they barely sit. Now we'll come to the now we'll understand the two LIGO sites and how the coincidence detection occurs. Now, LIGO is actually two detectors. Um, it's Hanford in Washington and Livingston, Louisiana, which are 3,000 kilometers apart. And that's not an accident, it's a whole strategy. Now, for example, everything shakes a mirror. Trucks, earthquakes, ocean microseisms, hundreds of kilometers away. To a single detector, any large transient looks like a potential signal. And this false alarm is a huge problem for us. Now, the solution is actually coincidence. A genuine gravitational wave arrives at both sites within 10 milliseconds. The light time travel across 3,000 kilometers. One detector only detects, meaning it's local noise, which is discarded. Now, when both the detectors detect it at the same time, it's a gravitational wave. The single requirement slashes the false alarm rate by orders of magnitude. Now, we add a third site, for example, Virgo in Italy and Kagra in Japan, into the network, and the time delays between the three or four sites let you triangulate the source direction, giving astronomers a specific path of sky to point their telescopes at within minutes of detection. Now we'll get into the DSP aspect of it, where signal processing comes into picture. Now, there are five stages stand between a photon hitting the detector and a paper in physical review letters. Now, the stage one is ADC and calibration. Now, the photodetector output sampled at 16,384 hertz, which is nothing but 16 kilohertz. But raw voltage isn't strain. It's a complicated function of the entire instrument's optical and mechanical response. Calibration applies the inverse transfer function in real time, converting raw displacement into the actual strain h of t. Stage 2 is the noise conditioning. This calibrated data is still dominated by known noise, which is 60 Hz power line harmonics, mirror suspension resonances, and scattered light artifacts, all attacked with dedicated filters before any signal search begins. Now, stage 3 is the match filtering, the core algorithm. We cross-relate the clean data against a pre-computed library of every waveform shape that general relativity predicts for different source parameters. When data matches a template, the output peaks. This is where the astrophysics re-enters signal processing. Stage 4 is the trigger veto and ranking. The chi-square test checks whether a candidate's energy distributes across the templates the way a real gravitational wave would, coherently. Now, noise glitches dumps energy inconsistently and fails. Survivors of this test gets ranked by statistical significance. Now, the last stage is the Bayesian inference. A vetted candidate gets the full treatment. A statistical algorithm samples the posture probability distribution over all 15 physical source parameters simultaneously, giving us not just one point estimate but proper uncertainties on everything: masses, spins, distance, sky location, and orbital orientation. Now comes the actual enemy of the entire thing: noise and conditioning. It has three completely different phases depending on what frequency you're looking at. So the first is the below 30 Hz seismic noise. At 10 Hz, ground vibrations are 10 billion times larger than the gravitational wave signal. Now, each pendulum stage acts as a mechanical low pass filter. Four cascaded stages multiply the attenuations, giving suppression scaling as the fourth power of frequency. Combined with the active HAM ISI platform, 12 orders of magnitude total suppression are achieved, and this is barely enough. Now comes the second band, 30 to 200 Hz, which is thermal noise. The fluctuation dissipation theorem states that any material with mechanical noise exhibits random thermal possible fluctuations. Brownian movement. Mirror coating suspension fibers test masses all jitter. You cannot eliminate it at room temperature, which is exactly why we need next generation detectors which will cryogenically cool their mirrors to 10 to 20 Kelvin. Now comes the above 200 Hz short noise. Photons arrive randomly, Poisson statistics, creating unavoidable power fluctuations that mimic strain. More laser power helps, but more power means more radiation pressure, backward noise at low frequencies. Now that trade-off is called the standard quantum limit. It reduces one and the other rises. You cannot engineer around it with classical light. Hence, you need other techniques. Such techniques are called DSP filtering techniques for noise mitigation. Now, four filter families takes on these noise sources. First is the notch and comb filters. They remove 60 Hz power line harmonics and mechanical resonances. The IIR bikewood designs with Q factors from 100 to 1000, extremely narrow notches that cut only the problem frequency without touching adjacent bands that might contain a real signal. Next is the widening filters, which address a fundamental mismatch. Match filtering assumes white noise, equal power at every frequency. LIGO's noise is anything but enormously more power at low frequencies. So we divide the data by the square root of noise PSD in the frequency domain. Flattening the spectrum, we manufacture the assumption the math requires. Next is the bandpass filters, which is 8th order Butterworth filters, which enforce 20 to 2048 Hz band. Below 20 Hz, seismic noise still overwhelms everything. About 2 kHz, there are essentially no astrophysical signals and the noise is rising. The Butterworth design gives maximally flat response in the passband with a smooth roll-off. No ripple, no ringing. Vinyl filters are the fancy trick. Over 2,000 auxiliary sensors recording every environmental disturbance. The filter learns the linear relationship between each auxiliary channel and the noise it injects into the mainstream channel and then subtracts it. Noise cancelling headphones for a physics experiment, but expe- except the reference mic is 2,000 sensors cancelling noise from the cosmos. Next comes the match filtering aspect, which is basically the core algorithm of the entire thing. So match filtering is the optimal linear detection technique known for a signal buried in Gaussian noise. Optimal isn't the marketing. The Neyman-Pearson theorem proves it mathematically. Given any detection threshold, match filtering maximizes the probability of detecting a real signal while minimizing the probability of a false alarm. Nothing does better, which is proved as well. The SNR formula, which is Fourier transform the data, multiply by the conjugate template, divided by the noise PSD, and integrate the entire thing. The division by S of n, Sn of f is the key. Frequent frequency dependent weighting that automatically penalizes noisy bands and trusts clean ones. Now, the result is single optimal number. How much does this data look like? This template, weighted by where the detector is reliable. In practice, fast Fourier the data, Fourier transform the data, FFT, compute template in the frequency domain, multiply by the conjugate template over noise PSD, 1 multiply per bin, inverse FFT, the output is an SNR time series, 1 value per millisecond. Peak above 8 trigger. The chi-square test checks coherent energy distribution, which is real signals pass and glitches mostly fail. Repeat this for a million templates simultaneously and you got the answer. Now comes the template banks and the waveform approximants. Now I'm sure everyone must be thinking, why do we use a million templates? Now waveform shape changes significantly with mass and spin. Two 10 Two 30 solar masses black holes produce a single chirp with then 220 at the same total mass. Now when we miss the template, we miss the signal. Now this bank guarantees a minimum match of 97%, which means no source loss more than 3% of its optimal SNR wherever it falls in the parameter space. Now there are five families in these template banks. First is the post-Newtonian one, which expands Einstein's equation in orbital velocity and accurate for early inspiral. Next comes the effective one body, which maps the two body problem into one particle in an effective metric, which is valid into the merger. Then comes the IMR phenom X, which is frequency domain fit into NR, fast and complete. Next is the numerical relativity. They directly solve Einstein's equations and which is the gold standard and which takes weeks per waveform. Next is the surrogate models, which are neural networks trained on NR, which generate templates in microseconds. Now, machine learning eats the entire problem from the inside. Next comes the advanced DSP techniques. This is the part where engineers start bending the rules of physics itself. Now, everything in match filtering depends on knowing the noise PSD accurately. If your noise model is wrong, your SNR values are wrong. Hence, your detection thresholds are wrong, and your entire science is wrong. But LIGO's noise is non-stationary. It drifts over minutes as beam alignments shift, thermal states evolve, and environmental conditions change. So you need a noise estimate that updates continuously. Now, LIGO uses the Welch method, which is 50% overlapping hand-windowed segments, periodograms average. Now, the 50% overlap reduces the variance. Critically, a rolling median and not a mean. A loud transit glitch inflates the mean PSD and corrupts the match filter across that frequency band. The median is robust to single outliers. One statistical choice that saves the whole pipeline. Spectral lines, which are 60 Hz harmonics, pendulum resonances, and calibration lines, which are handled by baseline, which fit the PSD as a smooth continuum plus sharp Lorentzian lines simultaneously. You're not noticing the data and discarding those frequencies. You're modeling the noise there and honestly, so the match filter weights them correctly. Now the advanced DSP and the quantum noise reduction. Now, four techniques that go genuinely beyond classical signal processing are: first is quantum squeezing, the one that makes physics grin. Heisenberg's uncertainty principle means phase and amplitude uncertainty in the laser field have a fixed product, the standard quantum limit. A standard coherent state splits into equally, both show up as noise. Now, but quantum optics lets you squeeze, redistribute uncertainty from phase into amplitude. Reduced phase noise means reduced short noise at high frequencies. Since O3, LIGO injects squeezed vacuum states into the output mode, gaining 3 decibels, equivalent to doubling the laser power, without actually the thermal distortion that would come with it. Quantum mechanics is beaten by quantum mechanics. Next is the auxiliary subtraction. 2000 sensors, Wiener filters, correlated noise removed. Next is the deep learning aspect. Gravity Spy is a CNN and trained with citizen scientists, which classifies glitch morphology in real time. Next is the Q transform, which is modeled wavelets at multiple resolutions, which gives the time frequency picture. Now, the GW150914 chirp sweeping upward on a Q transform is one of the most iconic images in modern physics. Next is the online search pipelines and algorithms which were used to detect gravitational waves. This is six pipelines running continuously. PyCBC, which is match filtering with time slide false alarm estimation. GST LAL, real time SVD compressed templates, sub minute alerts. SPIIR, GPU IIR, match filtering sub second latency. Coherent wave burst, which is no templates and any coherent excess power, which is ideal for unknown sources. RIFT is full Bayesian postures in hours. When black holes merge a billion light years away, you want telescope alerts in a minute. And RIFT does this. Next is the detection and inference. Basically, the moment where it all actually started, the first detection. Now, on September 14, 2015, the LIGO had been back online after 4 days since its advanced LIGO upgrade. Now, the Livingston registered a chirp, which is 35 to 150 hertz in 0.45 seconds, which is the exact signature a binary merger final covalence does. Now, the Hanford registered the same signal 6.9 milliseconds later, which is the correct time offset for a wave arriving from the southern sky at the speed of light. Now, the network SNR was 24.4 was threshold is 8, which is not marginal. And the source was actually 36 and 29 solar masses combined into 62, with 3 solar masses radiated as gravitational waves in half a second, briefly exceeding the combined luminosity of all observable stars. And the distance was 1.34 billion light years away. The significance of this all was 5.1 sigma, and the false alarm rate was 1 per 203,000 years. Now, the team had spent 5 months running every conceivable check before announcing on February 11th, 2016. And the Nobel Prize of Physics was awarded to them also in 2017. Next comes the Bayesian parameter estimation, what DSP extracts. Now, detection is step one, science is step two. Full Bayesian posture over all 15 parameters simultaneously, two masses, two spin magnitudes, four spin angles, distance, two sky coordinates, inclination, polarization, covalence phase, and time, all at once with proper uncertainties. MCMC is random walk through 15-dimensional space 10 to 100 million steps, spending time proportional to posture probability, thorough but days on a cluster. Now, nested sampling in Bilby is more efficient and computers computes the Bayesian evidence for model comparison simultaneously. RIFT basically is fixed likelihood grid postures in hours. Normalizing flows is deep generative models postures in seconds. What once took weeks now finishes before the telescope stops slowing. Now we'll get into the future and the impact of generation of the detection of gravitational waves. Now, what comes next makes LIGO look like a prototype. Over 100 detections, the gravitational wave astronomy community treats this as just the start of the detection of gravitational waves. The future first of it is Einstein's telescope, underground triangular 10-kilometer arms, which eliminate the surface seismic noise. And triangular means three overlapping interferometers that simultaneously measure both gravitational wave polarizations. Cryogenic mirrors at 10 to 20 Kelvin beat thermal noise, and the xylophone optical configuration, which is two interferometer systems, one per frequency regime combined, and 100 times LIGO sensitivity. Now, binary black hole mergers anywhere in the observable universe can be detected. Next is the Cosmic Explorer, the American Vision, which scale the arms up 20-kilometer and 40-kilometer arms. Silicon test mass instead of fused silica enables cryogenic operation without excess absorption. Sensitivity extending down to 5 Hz and reaching stellar mass black hole mergers at redshift Z greater than 100. Next is LISA, three spacecrafts equilateral forming an equilateral triangle 2.5 million kilometers per side. Millihertz frequencies, which detect supermassive black hole mergers, millions of compact binaries in a galaxy, possibly the Big Bang gravitational wave background as well. Now, the DSP challenge is that the arms aren't rigid, they flex by kilometers. You cannot directly interfere the beams. Now, the time delay interferometry synthesizes virtual interferometers by combining all six one-way laser links with calculated time delays, cancelling laser frequency noise 10 times louder than the signal. Signal processing as the only thing standing between science and noise. Now we've come to the end of the video, and now let's bring this home and understand what we've talked about throughout the video. Now, in the start, Einstein had predicted gravitational waves in 1916 from geometry of accelerating masses. In 2015, we measured them a strain to 10 to the minus 21, a displacement 1,000 times smaller than a proton, across a 4-kilometer arm. We built that arm in a field. We measured the displacement with light. We did it with whitening filters that manufacture the white noise assumption match filtering requires. Match filtering cross-correlating a million templates against continuous data every second of every day. Probably optimal by the Neyman-Pearson theorem. Chi-squared vectors distinguishing coherent astrophysics from incoherent instrument artifacts. Bayesian inference extracting 15 physical parameters from a half-second signal in 15-dimensional parameter space. Quantum squeezing redistributing Heisenberg's uncertainty principle to beat the standard quantum limit. Neural networks trained by citizen scientists classifying glitches in real time. Wiener filters using 2000 auxiliary sensors simultaneously to subtract correlated noise from the main channel. And doing all of this, we didn't just detect a wave. We opened a new window to all of astronomy for all of human history. Gravitational waves pass through everything and they carry information from the darkest places where light never escapes. We have 100 events today. Future detectors will log millions per year, and we are going to learn things about the universe that we cannot yet even formulate the question for. And DSP transforms this noise dominated data into cosmic discoveries. This is engineering at its most profound.